Good morning. My name is David Deshpande. I'm a postdoc in the Kobayashi group at Northwestern University, and today I'm going to talk about some of our work in building a atom interferometer at Northwestern for doing precision measurements of gravity. Now, let's start with some motivation. So, despite like a century of quantum mechanics and general relativity being around, we still don't have a quantum theory of gravity, assuming such a theory even exists. But nonetheless, there has been a considerable amount of theoretical effort in things like string theory and loop quantum gravity. Now, the ambitious nature of these theories sort of make it very challenging to perform tests to prove them. So, alternatively, there are some other models, like for example, the Schrodinger-Newton equation, the DOC-Penrose model, and the Carl-Hizzi model, which are a little less ambitious, but they allow us to perform some tests with the available technology. Now, one such technology is atom interferometry. And I'd just like to use this cartoon to just highlight, give you a flavor of what could constitute an interplay between quantum mechanics and gravity. Now, we already know from atomic physics that optical atomic clocks have reached such a precision that even a few centimeters of vertical separation can cause a change in the frequency of the clock. So imagine if you were to take an atom interferometer and split two arms vertically enough by, let's say, a few meters, then we would see a measurable shift in the clock frequency. This would lead, it's predicted that this would lead to a decoherence in this quantum mechanical system, and the source of this decoherence would be gravity. All right, so atom interferometry at a level where we can test this. Now, I'll show you a few examples which suggest the answer is yes. All right, so very recently, a separation of wave packets in an atom interferometer was achieved at the half-meter scale at a 10-meter atomic fountain in Stanford. Shortly after that, the gravity gradient from a proof mass of size almost equal to the separation between the wave packets was measured. And also the same apparatus was used to measure to test the equivalence principle down to the 10 to the minus 12 level. Now, an upgrade of this apparatus is known as MAGIS 100, which utilizes the clock technology to measure gravitational waves. Now, but one could in principle also use these clocks to see the decoherence that I just described in the last slide. Right. So another one is precision measurement of G, which has been done very recently, down to the 150 parts per million level. All right, so first a brief overview of atom interferometry. So it is the atomic equivalent of the Mach-Zehnder interferometer, where a cloud of atoms is split into two paths using a pi over 2 pulse, and reflected using a pi pulse, and then recombined again using a pi over 2 pulse. This real space diagram shows you the trajectory of the atoms during free fall, and at the end, the atoms are imaged on the CCD camera, and the probabilities of the atoms in these both ports are fitted to this, and then delta phi, which is the phase difference, can be extracted and used to infer some physical properties of the system. Now, for a fixed phase resolution, little g can be measured to even more precision if delta z and delta t are maximized. So a longer baseline is typically preferred. All right, so the atoms we're using are strontium, and here's the electronic structure where we have a strong optical dipole transition at 461 nanometers, which we also use to cool down the atoms via Doppler cooling to roughly 1 millikelvin, with the help of some repump wavelengths. And then there's this narrow transition at 689 nanometers, which is about 1 micro, which will allow you to get your atoms down to roughly 1 microkelvin. Now, I'll just mention in passing that there's this 698 clock transition, which is suitable for gravitational wave detection, and that's because of the fact that there's this long-lived state, which has more than 100-second lifetime. But I won't be talking about this in this talk. I'll mainly limit the discussion to a 2-photon Bragg transition at 461 nanometers. Now, here's how the Bragg transition looks. We start off in a given momentum state of the electron, and absorb a photon to a virtual state that is tens of gigahertz detuned from the 1p1 state. That's followed by an emission of a downward propagating photon. And then as a result of this process, the atom has effectively gained 2 photon momentum kicks. And for this, like, we have bit delta detuning that is about 30 gigahertz, which is a factor of 1,000 greater than the natural line width of this transition to minimize the spontaneous emission from this upper level. And the small delta, which is typically of the order of tens of megahertz, is used to detune, it is used to compensate for the Doppler shift. And this process can be further continued and to achieve like extremely large momentum. And this is going to be a very key ingredient in achieving the large wave packet separations that I alluded to before. Now, just to give you a feel for like some of the numbers here, so the 1 photon momentum kick is about, it gives you about 1 centimeter per second increase in velocity. The launch height of our apparatus is about 2 meters, and typical Rabi frequencies in the 20 kilohertz range, and we're aiming for a total momentum separation of 100 h bar k. So that means that if in a 2 meter fountain for which half a second is a reasonable flight time, we could get up to 1 meter per second separation in momentum, which means that we could get up to half a meter separation, which is what we saw before. All right, so, but there's some caveats. Can we keep doing this forever? Well, the answer is no, because unfortunately, what comes to bite us is the AC Stark effect. Any kind of apparatus will have these ripples in intensity due to some defects, which unfortunately will travel across the baseline and diffract out, causing a energy landscape along the length of the interferometer, and that could contaminate our signal of gravity gradients that we're actually trying to measure from other proof masses. So one way to solve this problem is that if we add a spectator beam of equal power and opposite tuning to the main Bragg beam, then the opposite sign cancels this effect out. Now here's an overview of, here's a cartoon of our lab, which is approximately to scale. We have the optical table over here, a pit here. Inside the pit, we have our magneto-optical trap. On the left, we have our commercial atom source, and at the top, we have our 2 meter pipe in which we do our interferometry. And the lasers from this optical table are delivered to this pit and this top region using these optical fibers. So you have, once an atom is formed, it's launched up using a standing wave using the 2 counter-propagating beams. And then using a translation stage, a large proof mass is brought next to the atom cloud of the order of tens of centimeters all the way up to a meter. And once the atom has interacted with the proof mass, it falls back down into this imaging chamber where we can measure the phase difference. Now I'll go over these various subsystems one at a time, and I'll go through them in a chronological manner, where it's like what is, in other words, starting from the first step in the experiment to the last step of the experiment. So first we have our cooling lasers at 461 nanometers. They work as follows, where we have a master ECDL, to which this slave diode laser is injection locked, and the slave diode's light is split to the 2D-mont and the Zeeman lower, which I'll talk about in the atom source section. And then we have this other slave diode, which is used for the 3D-mont. And we also have these repump wavelengths because at this blue transition because of decay into these long-lived states. And then finally, we have a narrow transition to 1 microkelvin using the 689 nanometer diode laser. Here's a photo of our repump lasers and our 689 nanometer diode laser. Here's a ULE cavity to which we stabilize our interferometry lasers in the 689 nanometer transition for short-term stability. And for long-term stability, we rely on this atom source over here to the left by using saturation absorption spectroscopy. So here's our commercial atom source. It consists of an oven over here and a Zeeman-Slower consisting of tapered magnets and a 480 megahertz red to tune beam, which I showed you in the diode laser setup. And then finally, we have a 40 megahertz red to tune beam sent into these two ports where a 2D MOT is formed by retroreflecting an elliptic beam. This gives us a transverse velocity of atoms of about 3 millikelvin with a flux of 10 to the 11 atoms per second and an axial velocity of roughly 40 meters per second. All right, here's a photo of the atom source with all the optics necessary for implementing the Zeeman-Slower and the 2D MOT. All right, so I'll talk a little bit about the magneto-optical trap. Here's a CAD model showing the magneto-optical trap chamber with the 6 retroreflecting beams. The commercial atom source attaches to the MOT chamber over here. And because we want the anti-Helmholtz coils to be very close to each other because we want to achieve a high field of 50 gauss per centimeter, we have these special re-entrant or bucket-style flanges as shown in this picture over here. Here's a picture of one of our Helmholtz coils inserted into the bucket flange of the MOT chamber. And we've designed the setup such that it's nice and compact so that because we don't have a whole lot of space in the pit. So on the left we have the ion pump, which supports the weight of the atom source. On the right we have the TSP pump. And the optics that comes from the cables via fiber is then routed with this multi-deck breadboard structure and guided into the chamber. Here's a zoom in to show you what that looks like. All right, so because these components are still under construction, we decided to start with a temporary setup, and this setup is outside the pit for convenience. And it'll allow us to just debug the MOT faster. Here's a picture of our 3D MOT. Here's a zoom in. Right, so next I want to talk about the interferometry laser. Here's a photo of our commercial frequency double TISAF laser that gives us 461 nanometers at 1 watt power levels. Here's a reminder of the Bragg transition we're trying to achieve. We take the output of our TISAF lasers and then pass it through a double pass AOM for intensity stabilization as well as Doppler shift compensation. Then it's passed through a second pulse shaping AOM, which is then formed the upward propagating beam of this setup. And now another copy is made for the downward propagating beam. Now remember that we had to compensate for the AC start shift, and the way to achieve that was to achieve like tens of gigahertz of red detuning of a beam of equal power. So that's why we make a copy of this setup down here. All right, next I'll talk about the translation stage and the proof masses. Here's a CAD model showing the entire layout with the vacuum system in the pit and this tube, and the translation stages are located on these granite slabs for flatness and stability. Over here, you'll see 2 configuration of proof masses which can be moved in and out. And I'll talk about the relevance of these 2 types of proof masses in the test of the inverse square law towards the end of the talk. All right, so the measurement scheme is as follows. We have 2 atom interferometers separated spatially by roughly the order of the size of the proof mass. And this space-time diagram in the falling reference frame shows you how the momentum, how these 2 arms are separated in momentum and the space-time area enclosed by them. On the right, you have the same diagram but in the lab frame, and it's useful to look at it in the lab frame because the proof mass, which affects the local value of G, is actually not falling with the atoms. It's at rest. So then we can extract the phase after imaging, and then infer the gravity gradient delta T ZZ from this proof mass. All right. So the last step in this process is imaging. So here's a CAD model of our imaging chamber, where we have another re-entrant flange over here to increase the solid angle we get to image this atom cloud at the center. And you can also note that there's a bunch of other ports here would significantly enhance the optical access in comparison to the Mott chamber. Here's and then after this imaging system, the atoms are imaged on this CCD camera over here. The only thing that's constraining how much deeper this reinforcement flange can go in is when the laser beams which are traveling upwards and downwards do not clip with this port. All right, so how do we read out the phase? It's a technique called phase shear readout, in which, remember, we have two ports, and then at the last pi over 2 pulses in the sequence, we can slightly tilt one of the beams, and then that results in a horizontal spatial fringe pattern, which can be fit to these expressions, and in which case delta phi can be extracted in this form. And of course, you could also just compare the total intensity, but this allows us to suppress the atomic shock noise to a considerable degree. All right, so another way we can increase SNR, our signal to noise ratio, is to increase the exposure of the imaging beam to the atoms. But that unfortunately comes at a cost. If you expose them for too long, there's heating occurs, and we've done some simulations to predict that the interference pattern would wash out. So, as I said before, this imaging chamber has a lot of access ports, and one nice thing about it is that here we can slightly red detune the blue light, and with the same amount of exposure, we're able to preserve some of this interference pattern. All right, so the last part of the talk, I'm going to talk about some of the physics we're trying to study, and one of them is the measurement of big G. For context, here is the work that has already been done in the measurement of big G using torsion pendula. In the Brown's data points, you can see the same measurement using beam balances and two pendula. And finally, very recently in red, we got a data point from atom interferometry, where the gravity gradient was measured from these tungsten proof masses. Now, what we're aiming to do is improve this estimate by the precision by almost 2 orders of magnitude. All right, so the way we're going to do this is as follows. Now, I want to first talk about the test of the inverse square law, because it's very much related to the measurement of big G as well. That's because, for example, you can sort of think of it as precision measurement of big G as being like a special case of the testing of the inverse square law, where G is R dependent. As a reminder, here's the apparatus again, where we have a proof mass next to a cloud of atoms, and here I have plotted in solid black the contribution from the inverse square law. And in dashed red, you can see the contribution from a non-zero alpha and a finite lambda, which is the famous Yukawa potential. And if I then, with the use of my translation stages, move those masses out further, and then increase the size of the masses in a way such that I roughly keep the contribution from the inverse square law similar, but there's a big change in the contribution from the Yukawa potential. That's because if my initial and final points are like somewhere between the ranges of lambda, then that will cause a significant change in the potential from the Yukawa, the effect of the Yukawa potential. Now, in our case, we're interested in lambdas in the ranges of like, as I said, tens of centimeters to up to a meter, roughly. And what this curve here shows is the sensitivity to which the Yukawa potential can be the inverse square law can be tested using this model in the parameter spaceband by alpha and lambda. Now, alpha, how finely we can measure alpha? Oh, I forgot to mention that the gray shaded region is the one that has already been excluded by other experiments. Now, the precision to which we can measure alpha is determined by a couple of systematic effects. For example, the the precision in which we measure the geometry of the proof mass, the temperature of the proof mass, and some atomic parameters. Combining these all together, we get a uncertainty of roughly 1.7 parts per million, which is almost a 2 orders of magnitude improvement over the previous estimate. So there are some other experiments that we're also planning, and this is the primary experiment we're interested in. There are some other experiments that we can also explore. Is we can study macroscopic quantum mechanics because of the fact that we can achieve separations of the order of half a meter. And it's already been demonstrated that we have a proof mass that is roughly half a meter in size. We can see a gravitational curvature across the wave function of our atoms. Another cousin system is this larger 100-meter apparatus that is going to be used for, that is going to serve as a test bed for a potentially kilometer-scale gravitational wave detector using these clock atoms, which is something we're also involved in. And with that, I'd like to conclude the talk and thank my lab mates, and thank you. Question?
When you consider the advantages of using strontium or outlier in a Bragg-based gradiometer, is it primarily compared to alpha, is it primarily in the electromagnetic field sensitivity of the ground state, or are there other advantages?
Oh yeah, it is. It has a lot to do. I actually forgot to mention the main advantage of this is that we're not as sensitive to magnetic fields, not far from the experiment that I just showed you in my maintenance. There's a considerable amount of effort being put into magnetic shielding of the apparatus. So it's like, at least we will eventually do some amount of magnetic shielding in our smaller apparatus, but the fact that we're starting with the bosonic atoms helps us, makes our job a little easier. Yeah.
No question? So, yeah, thanks for the very nice talk. So you mentioned that the Yukawa measurement and the big G measurement are similar, although the systematics tend to be much harder for the absolute measurement of big G.
Right.
So how do you do a factor of 100 better? What was the limiting systematic for the...
So I believe there was, compared to, I'll have to from what I can remember from that paper that measured it to 150 parts per million, I believe spatially resolved detection was one of the systematic. Because if we can, and the fact that we can actually split the atom cloud into 2 parts, we know just based on the lasers, the laser wavelengths and the time it takes, we can know the exact length of the baseline with pretty good accuracy. The other systematic is that they use these very inhomogeneous tungsten masses, which unfortunately have density inhomogeneities that give rise to some systematics. And we are planning on using single crystals like silicon or
so you're using perfect millimoles in the proof masses.
Exactly, and then we also have to make sure that the surfaces are polished and nicely flat. Characterization is a very important component.
Thank you.
If you were to translate your uncertainty into a gravity gradient uncertainty at about 3 hertz to give you your expected repetition rate, do you know that number? Try to think of further applications.
Not off the top of my head. Sorry.
I'll talk about it.
Can we have 1 minute in question?